going into the postulates after all. What I've been finding the last couple of months is that when I get into having discussions with people with quantum, like Chris, is that they want to hear have a bunch of questions about quantum, and so I'm going to change the format somewhat and give some basic introductions to get some of us on introductions and to remind people what questions you might have about quantum, and then open it up for questions. I've got enough slides for a week's worth of presentations. I give presentations around the world all the time, but let's start there, and if we run out of questions, which I doubt if you will, is that I'll take it back over and I'll continue. So here's our speaking this evening, and it is being recorded, but I'm the only one being recorded. So if any questions any of you ask, please remind me to restate the question, because I'm cutting every one of you out just for all the legal nonsense we've got to go through anymore. All right, about me. I was in Silicon Valley from 1990 to 06. I worked at Apple OS 9 developer. I was a Netscape 3 and 4 developer. RSA, the encryption that is on everyone's phone and computers. You are now listening to one of the people that helped write that. I moved back here in 06, and a year later I started Logos, a few years later, I started Logos Solar. I've designed 350 of the solar installations you see around the valley, around the state. And if you know Phoenix pretty well, the Tesla supercharging station at the Biltmore is 90% me, and then if you go to Google Maps, the bank, the National Bank of Arizona, that's about a mile north of that, you'll be able to see that entire parking lot is covered. That was Solar City's project, but because I had an professional electrical engineering firm, they needed to have it signed. I'm the one that took it over, and within 5 minutes saved them over $10,000 and radically improved the aesthetics as well. So and then presently I have started another company called AZ Quantum Computing, and I've shared with you already some of the things that I'm doing. So that's the primarily Arizona technology evangelism, and then I'm a member of Mensa. So here's one of the main things to remember. Niels Bohr, about 70 years ago, told us, if you aren't confused by quantum mechanics, you haven't really understood it. And so no one really understands quantum mechanics at this point, and so don't feel bad if you don't either. So I wanted to start with one of the fallacies, with some of the misinformation that's spread about quantum computers. This one in particular is that they're 0 and 1 at the same time. Is this the? No. And so, it's not showing up. That's okay. And so this sphere, and this sphere are all technically the same thing. They're Bloch spheres, and they're just different representations of the same thing. And so what I'm showing here on the left is this is a classical computer. It's either a 0 or a 1. But when we come over to quantum computing, it goes to 3D and it becomes a Bloch sphere. And I wanted to give all three images to give you more of an idea of what it is. Is that, like I said, it's 3D, and so when we're being told that it is a 0 and 1 at the same time in a quantum computer, just take this point, for example, is that technically it's partly 0 and partly 1, and so they're claiming that is a 0 and 1 at the same time, which, as far as I'm concerned, is nonsense. Is that it's got a value of one or the other. It's got values of both, is what I meant to say. The other thing to let you know is that with quantum, it's probability. And so when we get into a value that might be all the way down here at the bottom, and we go and do measurement, as you all probably have heard by now, and the coherence collapses, and because we're taking the measurement, it does not mean it's going to go to the 1. From what little we know of quantum mechanics presently, that value can still go up to a 0. So there's one aspect of how things work. I'm going to bounce around here to give you a few ideas on things and comparisons. Quantum versus artificial intelligence, they both can handle and analyze huge amounts of data, but where AI gives general values such as the mean and averages and so on and so forth, quantum gives specifics. To give you somewhat of an example of what I'm talking about, quantum does optimization very well. One of the main things it does very well is optimization. DHL and Unisys are presently using quantum computers for tracking and planning where their packages are going to go. And so let's say that Peter is in Belgium and is sending me a package here. Is that within an hour or so, once the information gets in the system, is that let's say DHL will know the last mile of where it will be, what day it'll be shipped, what driver will be delivering it, what vehicle will be delivering it, and so on. That kind of specificity is where quantum excels. And there are three main types of quantum computers: electron-based, atom-based, and photon-based. To give you more description of that, is that I hope you can read it on any of the screens, but here are all of the technologies. And so when one asks what kind of quantum computer it is, here are the different types, and here are some. Because there's actually a total of approximately 70 different companies that are working in all these different technologies. And this one shouldn't be here because that's a cold atom. But otherwise, all that's correct. Yeah, go ahead.
Have any of these shown greater potential than others?
Let me flip that question. Some have shown that they don't have as much potential as others. And so one specifically that I want to bring up that is spoken about quite a bit is topological. With topological technology is that once you get your physics worked out, scaling it, which is one of the main two problems that quantum computers have, is easy to do. It's just essentially just add them all together and go. For the most part, that's oversimplification. But the problem with it, though, is to develop the physics of it. There are still some major problems with developing topological physics to get that going with the quantum computers. Otherwise, as far as what you're asking, inflection, Pascal Quera, PsiQuantum, which is at the Chicago Quantum Exchange, has a major installation there now. D-Waves is annealers, and those aren't fault tolerant quantum computers, but they're in existence now. And then Google, IBM, IonQ, and Quantinuum are the most major players right now. And then what's the one out of Canada? I always forget. Yes, thank you. And there's another 2 photonic quantum computer manufacturers. So those are presently the ones that we will hear releases every couple of months. Hey, we've achieved this. We've developed something that is now letting us utilize some quantum mechanics we weren't able to use before. We're able to utilize it. We've done enough research on it that we can now use it for our computers. And the nice thing that's been going on in the quantum industry is that everybody seems to share, other than Quantinuum that keeps things a little bit closer to their chest, which is, by the way, Honeywell out of here is where it started, is that everyone else seems to be sharing because there is so much to be done here. I mean, we're talking billions, if not trillions of dollars, I'll go into that in a minute, on developing these things. And so everybody knows, hey, the more I can help my neighbor, the more I'm helping myself, that type of thing. So there's your question. Is the other part of this too is some of these technologies are better than others. And so the nitrogen vacancy that I was, where is it? The nitrogen vacancy, Diatrope's doing as far as computers, but as far as sensors are concerned, that is pretty much a slam dunk when it comes to medical sensors. They're presently already built and commercially available right now. And as I was sharing with Stephen before we started the presentation, the level of resolution that we get with the quantum sensors, the new quantum sensors, is 10,000, 100,000 times greater. To give you one example of that, at the April presentation, I'm going to have a sensor expert out of San Francisco flown in, and one of the descriptions he likes to give is that MRI, which by the way is wave one of quantum, and I'll go into that in a minute, is that wave two sensors, wave one sensors with MRIs is like reading something under a street light, and so the resolution you have there. But if you go to a quantum sensor, it's like being able to read under the light from a candle a mile away, because the resolution is that much greater. And then here's a point that I like to share to help everybody start to get their heads around this a little bit more. This is regarding mainframes. The same type of thing happens with a quantum computer. And so when they describe having hybrid computers, that part of the processing is being done by a classical computer, yeah, that's true as far as the actual core part of the processing is concerned, but to a very large extent, much of the processing is being done by classical computers. So just like with a mainframe, you've got your pre-processing on a quantum computer, and all of that is done with a classical computer. Then you go to your processor, I'll go into this in a minute, and then you've got your post-processing. Because when the quantum computer does the processing, it spits out all this information, and it still needs to be analyzed and organized and so on at minimum, and oftentimes more than that. So what I'm getting at is in the same kind of scenarios, the same kind of general concept, very general concept of the way a mainframe is used, where just change this processor from being a mainframe processor to a quantum processor, and it's not much different than this. And hold on. And so here, now I want to explain to you how quantum computers work. So I hope, let me know if you can't hear this, so watch.
In a normal search, our agent tries to search every path randomly to reach the destination. And we cannot claim that the path we find is the shortest until we visit the entire search space. However, quantum search, you start with one agent, but whenever the agent becomes multiple paths, we send one agent to each new path. This allows us to search more.
Good, that's good.
The twist in this situation is that all those agents you see on the screen are just one single agent in multiple places. This phenomenon is known as quantum superposition. At the end, when we find a solution, all the other agents disappear, and the real existence of the agent is at the destination. It's strange, but that's how quantum computers work. When we compare agents, we can see that quantum computers can easily win, even with an increase in problem size. The complexity of the problem for a quantum computer will be winning. Share your thoughts on this.
So my thought on this is absolutely 100% wrong. This isn't the way it works. And so this, unfortunately, is part of the misinformation that's going out. When I got a hold of this, and I was one of the first people that did, fortunately, there was, on LinkedIn, there was already 10 to 20,000 people giving this thumbs up on LinkedIn. To get anything over 1,000 or even 1,000 on LinkedIn of anything, for those of you that know, that's just a huge number. This already had 10 or 20,000. And as I understand it, it doubled or tripled from there, and it's had 6 reposts as well. It's wrong. What they've described there as parallel processing, and quantum computers don't do parallel processing. Here, and I'll explain some more, but watch this next video.
It uses a names to explain quantum statements.
Let's look at a classical computer calculation for is painful. One by one, it has to have every single left turn, right turn, left turn, right turn, before it finally goes.
Same thing as we saw before.
Scans all possible routes simultaneously. This is amazing. How many turns are there? Hundreds of possible turns, right? Quantum computers do it all at once.
So 1 second. And so the only thing that I would slightly modify with this is that it doesn't still work its way through slightly. It does it literally all at once. It's like taking a photograph is that if you've got 2,000, you've got 2 billion possible ways to do it. It does all of them at once. Yes, Rhea? Rhea?
So with this type of methodology, is this kind of like the same, thought process and planning and design process that goes into like CPUs? Like if you're a big PC gamer like my husband and you need a very powerful computer to have a lot of graphics and everything, is, principles of quantum, computers used for that? Because I would imagine to have like a really powerful computer, you need like multiple pathways and everything to be able to, make sure the hardware works effectively.
I don't think that a gaming situation, I can't think of one, Stephen, maybe you can. I don't know of a gaming situation where quantum would work. Remember, it's going to be like think of anything that you would send to a mainframe or an HPC, a high performance computer, okay, or a high performance computer center, is that anything that you would send to those is analogous to what you would send to quantum. Only with quantum, especially, well, there's optimization and there's factorization are the two mathematically known avenues that quantum computers will be much better than classical computers, but anything intractable is when quantum computers really start to shine. And so now that you're bringing that up, that's a whole other issue, is that once they do make a calculation on something that's intractable, we then have to prove that it's a correct answer. We don't have anything to be able to verify it with. And so we run it multiple times, well, thousands and millions of times on that same computer, but we also run it on other technologies, as I've shown you. We run it on other technologies to ensure that we get the same answer. And that's the best we can do right presently to prove that the answers that we are getting with these quantum computers when they're trying to try to find a solution for presently intractable problems is how we, at least theoretically, practically are able to do it at this time. And so, did I answer your question? I took it further, but did that answer your question?
Yes, thank you.
Okay. Yes, Chris.
I think maybe explain that some workloads will be very good at quantum, and some like gaming might still need conventional accelerator.
Correct. And so there are one of the major two computers, and China tries to claim it's quantum, as does Quantum Computing Inc. that's up in Tempe and out of New Jersey, claims that they're a quantum company, and they aren't. And so what they're doing is that they're using light instead of electricity to get the calculations that are much faster than a typical classical computer, but they still aren't quantum. And so what I'm getting at is that type of thing, yes. And so the first wave here's some of the technologies. It's already generated tens of trillions of dollars for the planet. You can see all this. All of us have experienced these. It's not just MRI, it's nuclear MRI, lasers, solar, transistors, LEDs, atomic clocks, which then goes to mapping services, GPS, electron microscopes, polymers, and quite a bit more. And then here is a more encyclopedic list of what came with the first group. The second group is general categories because we still don't have this worked out. And the third one, this is the word third, and then I had a bunch of question marks down there because this is all up for guessing. And it's as much as the first to the second. When we go to the third, it's going to be even a bigger leap. And that's, I think, the end of my, hold on. And so what I think is going to happen is, because how it is now, we do probability with the first and second waves of quantum, is that when we get to third, I'm hoping that what Einstein said, what Tofte, the 2019 Nobel Peace Prizer for Physics, what Sabine Hossenfelder out of Austria has said as well, all of us agree that instead of making it probability, it becomes deterministic. And when quantum becomes deterministic, it's going to be a whole nother game. And so that's Greg's prediction for a third wave. And so anyway, here's my last slide. I mean, the last one's to tell about me, but here's what Richard Feynman, who's one of the principal scientists that has given us quantum computers and most certainly quantum mechanics. So from there's me, and fire away with questions.
So, going to maybe the question we asked earlier, some better than others, talk more about the conditions like superconducting being extreme cold, near 0 Kelvin versus trapped ion might be room temperature, and how are each of those maybe making progress? Because eventually we have to have these things in a practical world, right?
Correct. Oh.
Maybe repeat it.
Yeah. It was asked how the different technologies are progressing, and because some like superconducting require temperatures close to absolute zero, how those are comparing to other ones, and how they're being developed and how they're progressing, because ultimately all of these need to be able to work in a real world scenario. That's difficult. I mean, because I don't know where every one of them are. It's exciting to me to read about the new developments they have on a most certainly monthly basis. There's somebody that's coming out with something. As you say, is at least half these technologies require being near absolute zero. And that's obviously one of the things the companies are trying to work on to get it to warmer temperatures. Even up to 1 degree Kelvin is 1,000 times warmer than they are working on presently, working in it at the temperatures that we're working in. So I can't give you too much more than that because that's part of what the race is. Like I said earlier, though, is that there's some areas that some are going to be better. Like when we get to networks, photonics are the clear winner because you don't need to have any cooling or any different kind of environment for those. And so I don't know of anybody that's doing anything on networks. I mean, do you, Stephen? Other than photonics for networks?
Oh, yeah, we are.
Are you?
But, I'm just retired from the Center for Quantum Mechanics. I was on a Zoom call with a couple of our researchers in MIT, and they kept using the phrase they were to get a particular operations, actually the silver business and stuff. So, trying to kick their operation working at quantum room temperature. And they kept using this phrase quantum room temperature. And I don't like this phrase, I'm sorry, I didn't understand. Because the people with quantum here, they said, oh, 4 Kelvin. But this is it, and they were asking so runs it for so that is clearly something that can be commercialized.
But
20 millikelvin, that's really hard.
But notice what he said though too, is that's a very small network. It's within a hospital or a building. And so back to what I'm saying, when we get to mimicking or trying to completely update the internet with quantum technologies, it's going to be photonics. I mean, everybody that's doing anything on a larger scale, other than smaller like that.
No one here is ever going to have 4 Kelvin.
Correct. And so that's the reason. That's the reason I was saying it's going to be like a mainframe. Who have you ever heard? And we've had mainframes now for what, almost 100 years. And so who's ever had a mainframe at home? I don't care how rich you are, you just don't do it. Same kind of thing with a quantum computer. Well, maybe at some level because we can get into superposition and some other things that will work at a very small scale, like it's done within the human body. But presently, it's going to be like a mainframe computer, and that's the reason I was giving you the analogy earlier.
That feels kind of like a never say never, though, right?
Sorry?
That feels like a never say never, right?
Correct.
Nobody really
Correct.
conceive modern, is that 64 days enough for everybody? Right.
And that's the reason but I'll also put the time stipulation on it. I said presently. And so in the near future is what I was attempting to imply.
Well, there's a reason why it's that cold, right, for the coherence, right, and the stability. Once they work on that, it can get worse, so it's all, it will get solved. I think
that's what we're working on, yes.
What is Greg's guess and time frame when we'll see these things? Is it 2 years, 5 years, 10 years?
So the question is, what is Greg's guess on the time frame and when we will be seeing these technologies develop like that? Well, first of all, it's not going to be 2 years or even 5 years. Is the present timeline on quantum computers that has been published, and they no longer distort things. They usually are, the last 3 releases, they've made the numbers, the dates that they said they would make, and actually they've usually been a couple of months ahead of that. Those dates are 2029 and 2030 for a fault-tolerant computer and Q-Day in particular. And then I say Q, a few of us around the world say then the Q-Day will be that time, but then how much it affects you and me is still then another 5 or 10 years out, because there are so many other parameters that have to be considered on Q-Day, such as how long it takes to decrypt something, which takes days, the amount of money it takes to decrypt something, which takes, McKinsey says about $60,000 just to decrypt one bit of encryption. And so who's going to afford that? And then the number of quantum computers that are going to be able to do it. It isn't like we're going to have millions of computers around. You only have one, or maybe 5 or 6 or 10 or 20. I mean, so what? I mean, it's still way too small to start doing anything other than attacking another nation state. So that's many years away. Yes, Stephen?
You just touched on my question. I think this is the first quantum presentation I've seen in 5 years that did not have Chinese flag on it. So
okay. I'll be glad to. I'll be more than happy to. In fact, at our cybersecurity meeting, someone was from the federal government was doing something, and he came up to me because he said, "I heard you say something about quantum, Greg." And he said, "What about China?" And I said, "Yeah, what about them?" Anything regarding China is junk. All right. Think of a Yugo. Something worse than a Yugo. The things that they have done with the satellite transmissions is they send one byte of data, and they said, no, we can do all this, and that's ignoring all of physics, and it didn't transmit anything anywhere of anything other than they just did something that was so small it was useless. It was the same thing as when they said we broke RSA-20. We broke the encryption that all of you were using around the world, but it wasn't 2048. It was only 56 bits. Oh well, so what? I mean, I mean, it's so small, it's useless. So these kind of things are what I'm saying, is that China says they're doing something, but everything that they have done, and I mean everything. This is a technical person. It's not some average or something, but when I say everything, I mean absolute, is there hasn't been nothing, zero, that China has done that has created something new. They're good at evolution, but they are not good at making something new, and so quantum is a part of that. So did that answer your question well enough?
Let's keep it going.
Okay.
Let's assume that some subset of the companies on the slide here do develop working systems, and the Chinese, by whatever mechanism, whether it's reverse engineering or theft, are able to duplicate that and then start turning their crank. And they can turn that crank like that.
Right.
What happens then?
So the question was, what if China, by whatever means, legal, theft, whatever, acquires one of these systems after they've reached FTQC, fault-tolerant, a quantum computer has been developed? what happens then? Well, I haven't thought about that one, but your guess, I mean, you can guess where it might possibly go. My very first, I keep wanting to say there's going to be some technical problems in them developing it, even if they were able to get all of the information. But I don't know if that's true, because as you've said, is that they're good at making things, reproducing what's already been done. And so I haven't thought about it, but it wouldn't be good news. That's for sure. But then the other thing though too is well, one of the things you said, the question was if they reverse engineer it, and I'm claiming they won't be able to reverse engineer it because they don't have enough of the scientists at the level, and other things that I was implying earlier. It won't be a reverse engineering. It very possibly will be a theft. And again, that's a doomsday situation that I haven't thought about. And you could think about it as well as I could, because you're getting into huge amounts of data processing that's far greater than we're able to do now. You had a question?
Is there a baseline measurement that allows them to see if there's one quantum way working better than the other?
Excellent question. The question is there a baseline measurement that all the computers are tested on to see how well they're doing against other ones? This has been a decade or longer type of development that all companies have been asking to do, because you will see at least 3 or 4 of them here that will come out and say, here's an excellent way to test the quantum computers, and guess whose computer it says is doing better than everyone else's? It's theirs, and everybody else is doing poorly. And then some of the other ones will come out, and trust me, classical computers are not giving up without a fight. Is that many claims have been put out there, and those in the classical computer realm will come back and they'll say, look, classical computers can't do this calculation. It'll take it hundreds, if not thousands of years, and so on and so forth. Well, the computer scientists from classical computers spend a few days on it and come back and say, no, you're wrong. We can do this right now. I can run this on my classical computer, and it'll take a week, but it's not going to take, or actually they usually say it'll take a couple of days. And so it isn't that bad. But what I'm saying is classical computers is actually part of the run on trying to do this. So to answer your question, there isn't one. We've all been trying to develop one, so we could have a standard baseline like it's done in classical computers to see, to do apples to apples comparison with all of them, and we don't have one yet. Many people are trying to develop that for obvious reasons, but it doesn't exist at this point.
Yeah, nothing against classical computers against their own system.
Right, and then that's what I'm saying. It is just a base. It's a baseline for just quantum computers. That's what I'm saying. Yes, and then yes, of course we could extrapolate and see how some of those speed metrics we could compare to classical computers, but some of them are going to be intractable. Many of them are going to be intractable for classical computers. Ed, did you have a question? Ed? Oh, okay. Chris.
Yeah, and I appreciate the dialogue program.
Likewise.
So it's hard to separate the hype from reality. and by that, every day you will see some announcement that's, we just hit 5,000 qubits. I thought 100 qubits was a lot. Is that real? Or it's now possible to do this in Hamiltonian. Has that been proven? There's a lot of hypothetical claims, right? And, let's take Google Willow just said they cracked a quantum algorithm that would have taken 10,000 years. What was that? Is it true? Was it easy? Was it hypothetical? Can you break down some of the hype?
On that particular explanation, unfortunately, there are many advances that did make, and they're very legitimate, and those that are in the mathematical side of it and so on are saying this is absolutely pushed the boundaries much further than we had before. And unfortunately, I don't remember all the specifics of it, but it did do some things that were that no one's been able to do before. One of the calculations, though, that was hyped so much is somewhat bogus, because it's similar to what the Chinese claim, is that it was something that, okay, oh well, so what, nobody does this kind of thing or needs to do this. And so it's nice that they're able to do it, but it doesn't really push things. But again, there's at least 3 or 4 areas where they're able to do things. And one of those is that they started getting much closer to fault tolerant computations. Is that one of the other major problem with quantum computers is error correction. And so when you have a qubit that has X amount of problems, once you add another one to it, it's increasing it, so on and so forth. One of the major improvements that was found with the Willow chip is that they found that as they added further qubits to it, the number of errors were decreasing. And so this is the first company that's been able to do that thus far. And so then that brings up the next question, the next problem is that, okay, how do we scale it? And scaling is a major, major physics problem. And well, as of 3 weeks ago, most companies are claiming, no, it isn't a physics problem now. It is now an engineering, a logistics problem, and they've solved that. And most of us are hoping so, and that's extremely exciting because that's one of the major problems we have. So that's part of the reason many of us are thinking 2029, 2030, just watch out. That's when the bomb is going to drop, that, hey, somebody has reached, competitors had reached their equivalent milestone that matched that. So what I'm getting at is that even though, let's just as a hypothetical, IBM, because they've got more money than everybody else, is able to achieve a new milestone, what I'm saying is, don't be surprised if you've got another dozen of these companies coming out within a 1 to 2 years saying, hey, we've done the same thing with our technology as well. Yes?
Give me your question.
There.
Start with that. If I understand correctly, the law of observability affects how quantum mechanics work.
I'm sorry, I missed the first word. Say that, because there was
Law of observability affects how quantum mechanics works.
Yeah, you're getting into a deep topic. Go, keep going.
How does that affect quantum computing, or does it at all?
Very much so. Very much so. And so, again, this is a very deep topic, because I believe the scientist was John Bell, with Bell's theorem, that brought up, and still brings up, is that, let's start the very basic part of what you're talking about. He said, what is measurement? Define measurement. It isn't just us looking at it, and just because we as humans didn't look at it doesn't mean it's still collapsing. It will collapse. I mean, so if I have an instrument, a electronic eye of some sort looking at it, does it collapse then also? Does it collapse, on the other side of the galaxy? And just because we as humans didn't look at it. So, and I went off away from his measurement definitions, but he's written at least a half a dozen papers on what is measurement. And so even starting at the very basis of what is measurement is where we have to start when you ask that kind of question. And like I said, it gets really deep. We'll get into philosophy almost as much as we do physics. And so from there, then yes, of course it does, because we have to be able to measure the value. And so it's back to, it'll be a 0 or 1. And then when is that going to happen? How does that happen? And so, like, as I pointed out when I was giving the presentation on the zeros and ones, is that we don't even have a probability of where the value is on the qubit, even if it's clearly near 0, per the example I showed, that it's clearly near 0. Well, it's like 99.9% of the way to 0, and we do it decoheres, it collapses. We're still seeing it jump up to 1. We don't know what percentage that is. We have no idea when that's going to happen. And so, yes, it does affect it, but see what I'm getting at is that you're stepping into a question that is one of the biggest ones of all, that we have no idea.
I just didn't know if, putting the same question in several times to get the same answer at the same speed, or do you start getting variances because of that?
Well, okay, that's a different question, because now we aren't in the measurement. And so we have now defined the wave functions enough that instead of being the entire sphere of some sort, that when I put my value in, I know it's going to be within this range. And so, and then there's the probability that it's going to be there is because all of this is wave functions at this time. And so we're getting values that are consistent. And that's the reason when you do a run, that's not the word that is used, is that when it's run, the calculation is run, it's run thousands of times to ensure that we're getting the same value.
Thank you.
Yep.
What is a QPU? What will a QPU be?
Any one of those technologies. And especially if we can get it.
What is a practical, let's fast forward 2030. Are we talking about 10,000 qubit computing, or is it still around 100? Or like, what do you think is practical to do the things we can expect it to do? Right? We say quantum will be great at Python. Is that going to be 1 million qubits, or is it going to be 1,000?
Well, okay, you're bringing up at least two major advances, at least the direction manufacturers are going at this point, is that most, I don't know of any company that isn't, but everyone's going to logical qubits. And the reason they're going to logical qubits is because the net does error correction. So depending on the company, we're talking between 3 and 7 qubits will then make a logical qubit. And then the amount of error that qubit has, what the logical qubit has, is then decreasing every time I add another logical qubit with it. And so now, therefore, I can now start to combine my logical qubits and get and do scaling and get a larger system. So there's one aspect of it. But then the other part of that then is when they're combining the systems together, is that take a room at least this big and put a normal networking rack, or as many normal networking racks as you would have, take a normal networking rack and then put as many of those in this room, and every one of those is a quantum computer. And then you make all those talk to each other. And the reason we have to do that, because we don't have the ability at this point to put 100 million or even 1 million in one quantum computer at this point. We can put 1,000 or a couple thousand, but we can't get near 1 million. And so that's the reason this room would be filled with those racks, which would all be quantum computers. And there are some manufacturers now that have those cooling systems in them, that each one of those racks inside of it is down near zero. And then we have to network those together, and that's how many companies, that's the way many companies are presently assembling something like that to be able to get the scaling, which is what I mentioned earlier with your question about that being one of the major problems that we have, error correction and scaling. And so that's the main way that the most popular way that scaling is being addressed presently.
Maybe the follow that because quantum networking and the idea that having to get technically across the continent is involved in you quickly realize that sitting across the data center, getting across the room, is a significant technical challenge. So what that enables is then you could have 100 quantum computers with 100 qubits each. And that's a whole lot cheaper and a whole lot easier to develop than 1,000 qubit quantum computer. So if you get the same 10,000 qubits, you just have to chop it up into individual racks and then you're networking together, you can occupy.
And so he's given an example of one way to do the networking. Sure. And so that's bringing in the cost analysis. And so that's one way that some companies are addressing it. Sure.
Earlier we talked about China got their hands on these technologies.
you set up to collaborate on why you feel about it. And I'm not saying that as a approaching question at all. I'm just curious what you see coming.
Because essentially it becomes a weapon of war at that point. Is that
Like cryptography or like OODA loop or like what do you mean by that?
both, any of it. And so once someone has one of these computers, you're now able to solve intractable problems. So physics problems that you had on developing your latest and greatest ion blasting beam, or your the latest advances in lasers from wave 1, and we're now into wave 2 of making lasers that are now ultra powerful, and so Star Trek becomes possible, to absolutely starting, breaking some forms of encryption. Obviously, there are many forms that aren't, and those are the new NIST standards. But and then take it. Your mind can run and answer that as well as mine can. In that, think of some way that you can create malware or any of the ways that cybersecurity is being obstructed, slowed down, or completely taken apart, or burying something inside of it. You've now got something of super intelligence, or of calculating in a way that wasn't dreamed of or thought of previously. And so those are just thoughts off the top of my head. I'm sure if two or three of it, well, just you and I sat down for a while, we could think of a couple hundred. So that's what I'm saying. How are we doing on time, Peter?
We can go on and solve up to everybody's needs. Are there any other questions? If not, we would have to continue with the Q&A here. We can go to Lois and Nora and handle the conversation with the hearing here. Anything else?
On like the practical level for observation space, especially for regular physics or individuals, what are kind of the possibilities for all quantum computer? Whatever matters.
So the question is, what are the possibilities, the value to private industry? One of the other main areas that quantum computers have already been, at least mathematically proven, that will be accelerating things is material science. So Google has protein fold 3 with AI. Quantum computers in the lab have already been proven that they can go way beyond that already. So there's one example. So any intractable problems, present intractable problems, and again, material science, molecular modeling, molecular simulations, and so on and so forth. Take the human body. You're in biosciences, that how it's almost impossible now to be able to simulate even a cubic eighth of an inch of any part of the body, because there are too many processes going on at the same time between blood flow, nerves, so on and so forth. Expand that. And so I'm not saying that you'd be able to do the entire body, which is still way too big. Well, maybe, but instead of being a cube, an eighth of an inch on the side, is that make it 5 or 6, 10 inches, or a complete aspect of the body. And so I can now simulate the entire nervous system at once, which obviously presently isn't possible. And I mean all the way down to the atomic level when I'm saying simulation as well. And that includes everything. And I mean, we're talking fluid, all the fluid flows, not just blood, and then all the electron flows for electricity, and then magnetic aspects, and then superposition that we know is going on in many parts of the body. Incorporate all those. And so that would be for your field anyway.
In terms of the simulation, isolate one part of your body system, whether it's fluid
Right, right. And that's intractable with classical computers, correct.